This is Chapter 11, Section 1, Parametric Equations. This section may seem pretty easy, but make sure that you understand what's going on, what all these details tell us, because this is the foundation for 11.2, which we're going to do calculus upon these parametric equations. And if you're not really understanding the details, it can get confusing. All right, but now I actually think this is an easy chapter 11. But it gets very confusing for some people, so pay close attention. So before we talk about parametric, this is your standard equation that you have done always. And all we did is plot points, found the y values, so you plug those in, you get -1, 1, 7, 18, 17, plug in 4 is 31. And then you graph these points, and you would get a graph. So 0, -1, 1, 1, 2, 7, 3, 17, 4, 31. And if you connect those, you would get a curve. It actually comes out to be a parabola, because we know that's a parabola, right? So what is parametric? Here's parametric equations right there. And what's different? X and y are defined separately through a third variable t called the parameter, therefore parametric equations. So here, usually t will be given a starting and an ending t, and you will just pick points to represent what it's going to look like. So 0, 1, 2, 3, 4. I mean, I could have done more points, 0.1, 0.2, 0.3. I could have done as many as I wanted, but I'm just doing these 5 points. So here you'll notice t and x are one and the same. So if I plug in 0 for t, my x will be 0. Plug in 1 for t, my x will be 1. So I just keep on plugging t into the x equation and get my x values. For the y, I plug in 0 for t, and I get -1. I plug in 1 for t, and that will give me 1. I plug in 2 for t, that will give me 7. I plug in 3 for t, that's 18 minus 1, that'll be 17. And I plug in 4 here, that'll be 32 minus 1, which is 31. So now I have a bunch of coordinate pairs, x and y coordinates. But you'll notice all of these are the same as these. So when we plot this, we get the same graph, but a very big distinction. We started this graph at this point, and it has a motion to it. It's moving to the right, and this is the ending point. So there's a directionality to this parametric that the regular graph does not have. Very important to know. And so usually in this chapter or in this section for calculus, in the context, this is usually like a position of an object. And as time goes on, that object moves to new positions. So at any one point, now you're going to have a velocity in the x direction and a velocity in the y direction. Same thing with the acceleration. So a lot more details. And at different points on the graph, you will have different velocities. So that's what's going on. Here's your start, here's your end. When we did the original, there was no start, there was no end. And you had a whole parabola and it went forever. Here, you have a start and an end. So in the next one, I have another parametric equation. I'm going to give you a start time and an end time. So I'm going to go from 0 to 2 in this case. And I'm going to pick weird values. I mean, you can go 0.1, 0.2, 0.3, all the way to 2. But I'm going to pick some specific points because I want to. I'm going to pick those. Plug in 0. 0 squared is 0. Easy. Plug in 1. 1 squared is 1. Radical 2 squared is 2. Plug in radical 3 squared is 3. And plug in 2 squared is 4. I'm going to do the same thing, plug in 0 here. That's going to be -1. Plug in 1, that's going to give me 2 minus 1, or 1. Plug in radical 2. Radical 2 to the 4th, that's going to be 4 times 2 is 8. 8 minus 1 is 7. Radical 3 to the 4th, that's going to be 9 times 2 is 18 minus 1. It's going to get me 17. And now I plug in 2 to the 4th, that's 16 times 2 is 32 minus 1 is 31. Now all that to say, notice these x and y's are the same as these x and y's. You end up with the exact same graph again, except in this case, the time is 0 to 2. This is representing 2 seconds or minutes or hours. That's 0 in this case. So even though you get the same graph, we have a different parameter, different time frame. So if you think about it, the velocity of the object would be faster here because it made it to the end in 2 units of time, where it took 4 here. So you're going to see that velocities and everything will be different, even though the graph looks the same. And there is a direction. Like if you didn't have these arrows, which way is it moving there? Is it moving right and up, or is it moving down and left? And so there's a lot of information in these parametric equations. So in summary, parametric has the form of an x and a y as functions of t. So these equations specify x and y in terms of a third variable t called the parameter, and it's usually t. It doesn't have to be t. And in our case, t often represents time. And you're going to be given an interval of time, a starting and ending time. And if you take every single t between these, you will form a curve, and you'll have x and y coordinates, as I showed you. So you have x of t, y of t as ordered pairs. And we're going to see them as vectors in the future lesson, but that's kind of what's going on there. So if you graph all these points that satisfy these conditions, these points will form a curve, as we saw earlier. And so we're going to just I already made a chart for you to save you time. And as long as you understand where it comes from. So I have a formula for x, a formula for y, and I have that there. So I plug in all these values in here to get my x values. You can double check, but basically you're doubling the t. So 0, 2, 4, 6, 8, 10, 16, 14, 8, 12, 14, 16. I don't know how to count. Then you plug in 0 here, you get -4. You plug 1 here, you get 1/2 minus 4, it's -3.5. And so we get this column, and I have all these x and y coordinates. So let's graph these points. This time I'll do it in a beautiful gold. 0, -4. Bam. 2, -3.5. Bam. 4, -2. 6, -0.5. 8, 4. 10, 8.5. 12, 14. 14, 20.5. 16, 28. And again, you see a parabola forming. But you need to understand there's a start and there's a direction that this object's traveling. And at each point, it's traveling at a different velocity. Because watch, this is the distance covered in the first 2 units of time. This is the distance covered in the last 2 units of time. See, it's moving faster at the end. So things that you really didn't think about are significant in these graphs. There's the graph. There's the one we drew. There's the actual. And again, start, a direction of travel, and an end. One more example and we're done. We're going to, wow, I should have put it to the side because I'm going to have to scroll up and down. So here is our next and last example. I have a x and y, and I'm going from 0 to 1. Now, look at these weird t's that Yoshida picked. Why would he do that? I will explain. 0 is easy. Cosine of 0 is 1 times 4 is 4. And 0, sine of 0 is 0, so 0. So we get the point 40. Why did I pick 1/12? Because I don't want to use a calculator. If I put 1/12 there, that's going to be pi over 6. And I know the cosine of pi over 6 radical 3 over 2. Radical 3 over 2 times 4 is 2 radical 3. And 2 radical 3 is about 3.5. Now, I didn't do it in my head. I just done the calculator. And then we put 1/12 here. These will cancel to pi over 6. Sine of pi over 6 is a half. A half of 4 is 2. Why did I pick 1/8? 1/8 here would get us pi over 4, which is a 45, and I can calculate the x and y. Why did I pick 1/6? 1/6 would give me pi over 3, which I know how to do. Cosine pi over 3 is 1/2. 1/2 times 4 is 2, and so on and so forth, and we get this whole table. I just picked values to get our standard angles. Pi over 6, pi over 4, pi over 3, pi over 2. 4 pi over 3. 4 pi over 3? No, 2 pi over 3. 3 pi over 4. 5 pi over 6. Pi. 7 pi over 6. 5 pi over 4. And all, I just went around the circle and got all my standard angles, and I got these points. So I'm going to plot these, and we're going to see what we get. So we start off with 4, 0. I can do that. Then we get 3.5 and 2. 3.5 and 2. I can do that also. Then we get 2.8, 2.8. 2.8, let's see, 2/4. 2, these are quarters. So 2.8, 2.8 is going to be 2.8, 2.8, right around there. And then we have 2 and 3.5, 2 and 3.5, then 0.4, and this continues, and we're going to have negative 2 and 3.5, or negative 2 and 3.5, and negative 2.8, 2.8, negative 2.8, 2.8, and then we're going to have negative 3.5, negative 2, negative 3.5, positive 2, sorry, negative 3.5, positive 2. And then negative 4, 0. And if you keep on plotting all these points, you're going to end up with something that looks like this here. My brain. Yeah. Well, it's supposed to be a circle. It's supposed to be. Watch this. I think it'll do it for me. Do it, 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 do it. Oh! I know why it's not a circle. Even though it's, oh, I can't get to work. Look right. Okay, I can do this. Watch. Let me just do an oval. My graph paper is not to scale. It's wider than it is taller, so it's not looking right. But it is, believe me, it's uh-oh. I'm failing here. Close enough. It's a circle. It just doesn't look like it. So what's interesting about this, at different times, that's the starting point. And as time goes on, it's at different locations. So in the calculus of this, you're going to find the location of the object at certain times. You're going to find the velocity at times, the acceleration at times. So understand there's a start and an end and a direction to this. And that is the end of the lesson.